Hello and welcome to the final video on Conditional Probability Chapter 2 for the Year 13 portion of the statistics for Edexcel's A-level content. So today we're going to have a look at how tree diagrams can be used to illustrate conditional probabilities, and of course we looked at tree diagrams in Year 12 as well. So a lot of this will be revision plus a few new bits and pieces added on as well, with a few worked examples to just talk it through and explain in a bit more detail. So before we do, almost as ever, let's get warmed up with a few warm-up questions. So here they are, 4 to attempt in total. So all these are based on calculus and straight lines. So pause the video here and try these on your own, and when you're ready to see the solutions, press play and I'll guide you through how you get the answers, and hopefully yours will match mine. Okay then, so let's have a look together at question 1a. So question 1, we're given that the function y equals 6x minus 4 over x squared, where x is not equal to 0. We need to find dy by dx. So first of all, I'm going to rewrite y in index form. So I'm going to rewrite it as y equals 6x minus 4x to the minus 2. So then dy by dx, I can think of this much easier now. Dy by dx, I just simply take 1 off the powers of x, so 6x, that's 6x to the 1 essentially, that becomes 6x to the 0, it just becomes 6. This minus 2 comes to the front and multiplies with that minus 4, so we get plus 8, and we take 1 off the power. So dy by dx is 6 plus 8, x to the minus 3. Then find the integral of y dx. This is going to be the integral of 6x minus 4 over x squared with respect to x. So we can just do each term piece by piece. So this one, we just increase the power of x by 1. So 6x becomes 6x squared over 2. This here, I would rewrite normally as 4x to the minus 2. In fact, I'm not sure why I didn't do that. So thinking of the 4 over x squared like this, I can then just simply increase the power by 1. So I'm going to call this minus 4 x to the minus 1, then divide by that new power, which of course is minus 1. This can be simplified, of course. And of course, we always need to remember, if it's an indefinite integral, we need to consider the constant of integration, normally big C. 6 over 2 becomes 3, so we have 3x squared. Minus 4 divided by minus 1 becomes positive 4. And x to the minus 1 we can leave as x to the minus 1. We could have wrote this 4 over x if we wanted, doesn't really matter. And then finally the constant of integration. So that's the integral of y with respect to x. Question 2. We have a curve with equation y equals f of x passing through the point 1, 6. We're given the derivative function is this. We now need to find f of x and simplify the answer. So f of x will be the integral of the derivative function with respect to x. So all we need to do here is to integrate this thing here. We're going to integrate all of this with respect to x. But what I'm going to do here, once again like in warm-up question 1, I'm going to rewrite it all in index form. So 3 I'm going to leave as 3. 5x squared divided by x to the half. When we divide using powers, we subtract the powers. So 2 subtract 1/2 will leave us with 3 halves. So as a single power of x, that's going to be 5x to the power 3 halves. And then 2 divided by x to the half is the same as 2 multiplied by x to the minus 1/2. So integrating all of this with respect to x. So 3 becomes 3x. 5x to the 3 over 2. I'm going to add 1 to the power, so it becomes 5 over 2. Then divide by the new power. Same with this 2x to the minus 1/2. Add 1 to minus 1/2 becomes positive 1/2. Then divide by the new power of 1/2. All of which we need to add c to. Then simplifying down fully, we have 3x. 5 divided by 5 over 2 is just 2. So we have 2x to the 5 over 2. 2 divided by 1/2 becomes 4. So we have 4x to the half plus c. But then what we need to do is to find out what this constant of integration is. But we know when x is 1, y is 6. So at this stage here, what we can do is we can sub in the value of x is 1. So if we just sub x being equal to 1, when x is 1, we need f of x to be 6, because y, which is f of x, is 6 when x is 1. So what is f of 1? Well, f of 1 is going to be 3x, which means 3 times 1, plus 2 times x. So 2 times 1 to the power 5 over 2. That's just going to be 2, because 1 to the power anything will give us just 1. So 2 times 1 is 2. 4 times 1 to the half is just 4. Then plus c. So in other words, f of 1 equals 3 plus 2 plus 4. 3 plus 2 plus 4 is 9. So f of 1 equals 9 plus c. But f of 1 needs to equal 6. So therefore, by taking 9 off both sides, we know it needs to be equal 6, because it says it goes through the point 1, 6. So if we take 9 off both sides of this, to get c on its own, we then can see that c is 6 take away 9, which is minus 3. So therefore, putting all this together, f of x is 3x plus 2x to the power 5 over 2 plus 4x to the power of 1/2 plus c, which we now know is minus 3. So that's the full function of x, including its constant of integration, which we needed to include as well. Question 3. We've got a curve, big C, with this equation, y equals 1/3 x cubed minus 4x squared plus 8x plus 3, and we're told that the point P, which is at 3, 0, lies on this curve C. Find the equation of a tangent to C at P, giving your answer in the form y equals mx plus c, where m and c are constants. So to find the equation of a tangent, we need to work out the gradient function. In other words, we need to take dy by dx. So if y is this, then dy by dx is going to be 1/3. Bring the power to the front, take 1 off the power, minus 4x squared, so that becomes minus 4 times 2x to the 1. 8x just becomes 8. So if you wanted to, of course, you can simplify this down yourself. I'm just showing you each step. So 1/3 times 3 is just 1. So we get x squared minus 4 times 2 is just minus 8x. X to the power 1 is just the same as an x, plus 8. So the point P is when x is 3 and y is 0. So we know that the point P lies on C, so we can substitute in when x is 3 to work out what the gradient is at point P. So when x is 3, what's the gradient going to be? So dy by dx will then be 3 squared minus 8 times 3 plus 8, just simply subbing in that x is equal to 3. So that's going to give us 9 minus 24 plus 8. So I would suggest using a calculator just in case, to make sure we don't make any silly errors, myself included, of course. 9 minus 24 plus 8 gives us minus 7. So therefore, the equation of this tangent is y equals minus 7x plus c. But we can substitute in the point P. So if we sub in when x is 3, y is 0, we can work out what this c is. So sub x is 3 when y is 0. Basically the coordinates of point P. So when y is 0, x is 3. So 0 equals minus 7 times 3 plus c. Minus 7 multiplied by 3 is minus 21. So 0 equals minus 21 plus c. Therefore, adding 21 to both sides, we get that c equals 21. So therefore, the tangent to c at P, so the tangent to c at P has equation y equals minus 7x plus 21. Part 4 uses the same information. So question 4 uses this same curve C. So another point Q also lies on C, and it says here the tangent to C at point Q is parallel to the tangent to C at P. Well, the tangent to C at P from question 3 had the equation y equals minus 7x plus 21. So that had a gradient of minus 7. So we need to find the coordinates of Q, and we're told that the tangent at Q also has the same gradient. So dy by dx, again from question 3, we had that was x squared minus 8x plus 8. So if the gradient at point Q is the same, it's equal to minus 7, what we could do is ask ourselves, where is this gradient function also equal to minus 7? So the point P, if we substitute in 3 into this expression, then understandably and obviously we'll get minus 7 as the answer. But what other value of x would give us a gradient function of minus 7? And that other point, that other coordinate for x, will be the coordinate at point Q. So if we just take this equation and add 7 to both sides, we then see that x squared minus 8x plus 15 equals 0, and this will now factorise nicely. So two values that multiply to 15 and add to minus 8, two whole numbers that fit that bill, would be minus 3 and minus 8. So minus 3 and minus 5, what am I thinking? Equals 0. So therefore, the values of x that make this work and solve the equation are x equals 3 and also x equals 5. Now, we know that x equals 3 works, so that's no surprise. What we are interested in, though, is when x is equal to 5. So when x is equal to 5, we can substitute in for what y is. So when x is equal to 5, y will be 1/3 times 5 cubed minus 4x squared, so minus 4 times 5 squared. Lots of colour changes here. Plus 8 times x, so plus 8 times 5, plus 3. So again, definitely use a calculator for this one. This is to find the y coordinate when x is equal to 5. So if we just substitute in here, so we've got 1/3, pardon me, 1/3 multiplied by 5 cubed. Whoops. Minus 4 multiplied by 5 squared, plus 8 times 5, plus 3. That gives us minus 46 over 3. So the coordinates of x is 5 and y is minus 46 over 3. So in other words, Q is when x is 5 and y is minus 46 over 3. So now that we're suitably warmed up, let's talk about today's tree diagrams in terms of probabilities. So, tree diagrams. Conditional probabilities can be represented on a tree diagram like so. So, imagine two branches for two different events. Now, the first branch, let's imagine this is representing the event A happening. So, in probability notation, the probability of A occurring is P brackets A, like so. So imagine that A has happened, then this second set of branches is a second scenario for what happens next. So let's say that either A can happen or not happen. So not happening will be down here, which I'll come to in a second. And the second scenario can be if event B happens or doesn't happen. So here, if event B happens, then we can say that event B's happened, knowing that event A has happened before it. So this is not only simply the probability of B, this here would be the probability of B given that A's happened. So this will be the probability B line A. So if B happened, this would be the probability of B given A. So when we can say here, if A and B happen together, the probability of A and B happening, remember from GCSE probability, we just multiply the probabilities along the branches we go along. So the probability of A and B, A intersection with B, would be the probability of A, this value here, multiplied by the probability of B given A. Alternatively, if B did not happen, this would be B dashed. And so the probability of B not happening, given that A did, would be P brackets B dashed line A. And so this would be given by this formula here. The probability of A happening and then B not is a probability of A multiplied by the probability of B not happening, given that A did. In a similar way, A dashed, if A didn't happen, that's probability of A dashed. And then if A didn't happen, B still can happen. So the probability of B happening, given that A did not, we'd label that probability B line A dashed. Or if A doesn't happen and B doesn't happen, this one here would be B dashed. And that probability down here would be labelled as P brackets B dashed given A dashed. And as an equation, we could write it like this. So let's now apply this to a worked example. So, worked example 1. This is an exam style question. So, a group of students were surveyed by a principal and 2/3 were found to always hand in assignments on time. When questioned about their assignments, 3/5 said that they always start their assignments on the day they're issued, and of those who always start their assignments on the day they are issued, 11 out of 20 hand them in on time. So first of all, draw a tree diagram to represent this information. So going back to what we just talked about in terms of the introduction to tree diagrams, we can use the same idea, but instead of using events A and B, let's use the event big S for the event the student starts the assignment on time, and the event big H stands for the event the student hands in the assignment on time. So instead of A and B, and A dashed and B dashed, like we had here, we can switch A for S and the event B for H, and likewise A dashed is S dashed now, and B dashed can be H dashed. So just taking this diagram here, but replacing it with S's and H's, we have this, which we can now think about populating with information from this paragraph. So let's talk this through step by step. So the first thing we can work on is actually the second sentence. The first sentence we can't actually tackle yet. I'll explain why not in just a moment. The second sentence says, when questioned about their assignments, 3/5 of the students said they always start their assignments on the day they are issued. And so, assuming this to be true, then the probability that the student starts an assignment on time is 3/5. So this value here, the probability of starting on time, would be 3/5. Now, the sum of all the values in each set of branches always needs to add up to 1. So if this is 3/5, this value down here must be the other 2/5. In other words, 1 take away 3/5 gives us 2/5. So we can add this on down here, like so. Next it says, of those who always start their assignments on the day they're issued, 11/20 hand them in on time. So, 11/20 hand them in on time, but only of those who started their assignments on that day. So, this is given that they started it on time, then the probability that they would then hand it in on time once they started it on time would be 11/20. So this 11/20 is actually the probability that they hand it in on time given that they started it on time. So we can add in 11/20 for this branch here. And if this is 11/20, because each set of branches needs to add up to 1, this branch here, H dashed line S, must be 9/20. So where to go from now? Well, we don't know these probabilities down here, so I'm going to call this branch X, and this bottom one down here 1 take away X. We can't work out what each branch is yet, because we're told on this first line about this group of students surveyed by a principal and 2/3 were found to always hand in assignments on time. these 2/3 that hand in assignments on time are split between these here, which hand in on time, and also these as well. So at this stage, that's as far as we can go with doing our tree diagram, and that's part A done for now. Part B, we're asked to find the probability that a randomly selected student always starts their assignments on the day they are issued and hands them in on time. And part 2, we need to work out these probabilities down here. Let's just focus on this first sentence now. So a group of students were surveyed by a principal, and it does say 2/3 were found to always hand them in on time. So there's two scenarios how that could be. So the student could start them on time and then hand them in on time. So it could be these students here, or it could be the students that actually start them late, but then go on to hand the assignment in on time anyway. So it could be this branch down here, which I'm going to highlight in purple as well. So the probability for B part 1 of always starting their assignments on the day they are issued and handing them in on time is a probability of S and H. It's this top line in purple as well. So it's the probability of starting it on time, which would be 3/5, multiplied by the probability of handing it in on time, given that it's been started on time, which is 11/20. So we're just going to multiply 3/5 by 11/20, and as a simplified fraction, that gives us 33/100. So this here we can fill in with a probability of 33/100, like so. Just returning to this same point, a group of students were surveyed and 2/3 were found to always hand in assignments on time. So essentially, this branch here, plus the probability of this other purple branch, needs to add up to 2/3. So in probability notation, P, S intersecting with H, plus a probability of not starting on time, but still handing in on time, this one here, needs to total 2/3. So filling in the information we know from B part 1 that P, S intersect H is 33/100, so we can add this in as well. Then from there, we can rearrange. But from here, just added in there 2x/5, that's because 2/5 multiplied by x is 2x/5. So this branch, 33/100, plus this branch, 2/5 times x, 2x/5, needs to give us a value of 2/3. We can now rearrange this by subtracting 33/100ths from both sides. If we do that, we see that 2x/5 is 101/300, and then to find out what x is, we can then times by 5 and divide by 2, just get rid of this fraction. So making x a subject, we have therefore that x has to be 101/300 times 5/2, which is 101/20. So what I'm going to do now, I'm going to replace x with what x actually is as a value. So x can go, and 101/120 comes back in its place. In the same way, this value here, 2/5 of x, I can just take this and multiply by 2/5. So what's 101/120 times 2/5? Let's see. 101/120 multiplied by 2/5 gives us a value of 101/300. So 2x/5 we can replace with 101/300. In the same way, we can also work out this branch if we wanted as well. 3/5 times 9/20. We'll do that later. If this branch is 101/300, what we can do next is say that this one's 19/20. That was 101/120. This will be the other 19/120. Like I said over here, 3/5 times 9/20. This branch will be 27/100. And then we can work out this probability in one of two different ways. We can either do 2/5 times 19/120. In fact, if we do that now, so 2/5 multiplied by 19/120. That gives us a total of 19/300. Or what we could do is realise that at the end of a tree diagram, all the probabilities must sum to exactly 1. So another way we could have done it, we could have added together these values and performed 1 subtracted that value. just for consistency, I'll show you that gives you 19 over 300 as well. So if I add together these fractions, 33 over 100 plus 27 over 100, and then plus 101 over 300, gives us 281 over 300, and then 1 subtract that value gives us 19 over 300. And so the probability of not starting on time and then not handing in on time would be 19 over 300. And if we have a look at B part 2, that is the actual question it's asking. So for B part 2, does not hand in assignments on time and does not start their assignments on the day they're issued, the probability of that would be 19 over 300. Like so. Which then just leaves us to tackle part C. So, question part C. Determine whether or not always starting assignments on the day they are issued and handing them in on time are statistically independent. Give reasons for your answer. So we need to remember what the definition of statistical independence is from year 12. So what we need to remember is this. So S and H are going to be independent statistically if and only if, that's what the double F is for, if the probability of landing in the intersection of S and H is equivalent to the probability of S multiplied by the probability of event H. Only then are the two events independent. So let's just work out the probability of S intersecting with H separate to probability of S multiplied by the probability of H. Then we'll see afterwards if they are equal or not. So first of all, the probability of S and H, which is the same as the intersection, is 33 over 100. The probability of starting on time and handing in on time is this top branch here, 33 over 100. The probability of starting on time was 3/5, which we had before, and the probability of handing in on time, according to the headmaster at least, was 2/3. And so 3/5 multiplied by 2/3 would give us 2/5. So is this probability the same as this one? Is 33 over 100 the same as 2/5? Obviously not. So we just conclude by saying because these two probabilities are not the same, therefore the two events S and H are not statistically independent. If these two were equal, they would be statistically independent, but because they're not, they're not. So let's have a look at a second worked example. Worked example 2. It's been imaginatively called. So there's two different bags containing different amounts of balls inside. So bag B contains 6 balls, 3 are red and 3 are yellow. The bag Q contains 7 balls, of which 4 are red and 3 are yellow. A ball is drawn at random from bag P and placed into bag Q. A second ball is drawn from bag P and placed in bag Q. So the same thing happens twice. 2 balls picked at random in succession from P into Q, both at random. But then the third picking is drawn at random from the 9 balls then inside bag Q, because bag Q started with 7 balls, but after 2 balls have been placed from P into Q, it will then have a total of 9. So this drawing is from bag P, then from bag Q. So the event A occurs when the 2 balls drawn from bag P are of the same colour. The event B occurs when the ball drawn from bag Q is red. But first of all we need to do is to copy and complete the tree diagram. So let's just think about this from the top going down. So just to be clear, because 2 balls are picked from P, I'm going to label this one, that's picked from P, that's picked from P, and this final one here is a picking from bag Q. So 2 balls are picked from bag P and placed into Q. So because 2 balls are going extra into bag Q, the total number of balls ending up in bag Q will be 7 plus 2, which will be 9. And so for bag Q here, the pickings will be out of a total of 9. So I'm just going to fill these in here. Then we can simplify down after, if we can. That one, we're already told that's a 5 out of 9 chance, so we can fill in this for definite as 4 out of 9. Same here, if that's 5/9, we know that must be 4/9. This bottom one here will be out of 9 too. So this very top branch, this would be if a red, then an extra red. So if 2 reds were placed from P into Q. There are already 4 reds in Q, so 4 plus an extra 1 and 2 would give us 6 reds out of 9. 6 reds out of 9, of course, simplifies to 2/3. That means the other 3 out of 9 balls would be yellow, which of course would be the other 1/3 of them. These have been done already, as of those. So we now need to go and consider this branch here. So the probability of picking a yellow first would be 3/6. So if we picked a yellow first from bag P, there'd then only be another 2 yellows out of a total of 5 to pick from. Therefore the total reds to pick from would then be 3 reds out of a total of 5. So this final branch, if a yellow was picked and then a yellow was picked again from P, so 2 yellows go from P into Q, that would mean the total number of yellows in Q now would be 3 plus 2, which should be 5 out of 9 yellows. Therefore the total number of reds would be 4/9. So that's our tree diagram completed. We can now use this to answer the next parts of this very question. Find the probability of event A. So let's just remind ourselves what event A actually was. So event A occurs when the 2 balls drawn from bag P are of the same colour. So there's actually 2 ways that could happen. So 2 balls being drawn of the same colour, it could be that the first is red and the second's red, or it could of course be that the second's yellow and then the other one's yellow. In fact, it may have made more sense if I'd have colour-coded this first one in red like so. But never mind. So the probability of event A happening is therefore the probability of having 2 reds plus the probability of having 2 yellows. So yellow doesn't stand out very clearly there, that's why I tend not to use it, but there we go. So red first, then red again, is a half multiplied by 2/5. And then we add on the probability of yellow, which is again 1/2 multiplied by 2/5. And if we work this one out, we should actually get 2/5. So the probability of event A happening is 2/5. Now let's think about what part C is asking us. Part C, it asks us to show that the probability of B is 5/9. So the probability of B, well, event B occurs when the ball drawn from bag Q is red. So there's actually 4 ways that could happen. It could be red, red, red for P, P and Q, or we could have red, yellow, and then red for Q, or it could be yellow, red, red, or the final one, we could have yellow, yellow, and then finally red, which, whoops, didn't want it to do that. So yellow, yellow, and then red. So this is quite a lot of fractions to add up. So this top root, the probability of having red, red, and then red, would be 1/2 times 2/5 times 2/3. Or we could go the green route, which is 1/2 times 3/5 times 5/9. Or the blue route, again 1/2 times 3/5 times 5/9. And finally the bottom purple route, which is 1/2 multiplied by 2/5 multiplied by 4/9. So just to complete the colour coding on here, so the first bit was yellow, the second route was green, then a light blue, and the bottom route was purple. So the thing we need to do now is very, very carefully indeed, just key this in on a calculator without making any errors. So we've got 1/2 multiplied by 2/5 multiplied by 2/3 for the first fraction string. So that's the first one done. Then we're going to add on to that 1/2 multiplied by 3/5 multiplied by 5/9. Now if we notice, this one in blue is exactly the same as this one in green. I can just multiply this whole thing by 2. So that'll do us for the green and the blue, because those two are equivalent. So we can just finally add together this purple one, 1/2 plus 2/5 plus 4/9. So if we do this one finally, so then plus 1/2 times 2/5 times 4/9, and then cross our fingers and toes if you're that able, which I'm not, see if you get the right answer. We'll then get a total of 5/9. So part C probability of event B is, as we needed to show, 5/9 as required. So next, let's think about question part D. So D, you have to show that the probability of A and B happening together is 2/9. So probability of A and B. So that means event A happening and also event B happening. So event A is the probability of the two balls drawn from bag P are of the same colour. And so then event B is when the ball drawn from Q is red. So if we have A and then B, that's essentially the same as saying that the first two balls are red, and then we have a red from Q, or we have yellow, yellow, and then Q. So event A can happen in two different ways. So what we can have here is it could be red and then red, and then B could be a red as well. So event A, two reds, event B, the final one from bag Q is picked a red, or it could be that event A happens for the first two balls not being both red, but both being yellow instead. So instead we could have yellow, yellow, and then event B of course needs to be that it's a red. So those are two ways it could happen. So the first scenario, red, red, and then red again, is quite clearly this first route here, which I'm just going to put in the yellow. So that's the first way of happening. Or if we have yellow, yellow, and then red, then that one is this route down here. So if we do this and add them both together, we have a half multiplied by 2/5 multiplied by 2/3, or a half multiplied by 2/5 multiplied by 4/9. So if we do this calculation and add them all together, so a half multiplied by 2/5 times 2/3 plus a half multiplied by 2/5 multiplied by 4/9 gives us 2/9. So next up is part E. Part E, hence find the value of the probability of A joined up with B, A unified with B. So we need to remember this law of probability. So probability of A joined with B, A unified with B, is the probability of A plus the probability of B minus the probability of being in the intersection of A and B. So we can fill in what we know. So from part B, we worked out that the probability of A was 2/5. We also worked out from part C that the probability of event B happening, in fact we showed from part C that the probability of event B happening was 5/9, so that's 2/5 plus 5/9. And then part D, the question we just did, we showed that the probability of A and B was 2/9. So it's 2/5 plus 5/9 minus 2/9. So if we just do this on our calculators. So we've got 2/5. 5/9 take 2/9. May as well just add on the 3/9 rather than doing unnecessary calculations. And that gives us 11/15. Then finally, part F. Given that all three balls drawn are the same colour, find the probability that they're all red. So this is probability all are red, given that all same colour. Well, the only thing that can happen is the probability of them all being red, and the total number of ways we can have it where they're all the same colour Well, they're either going to be all yellow or they're going to be all red. So, probability of all being red. So, for them all being red, that's going to be 1/2 times 2/5 times 2/3 at the top. So that gives us, let's see, 1/2 multiplied by 2/5, that's 1/5. 1/5 times 2/3, that gives us 2/15. And so on the top of this fraction we have 2/15 all over, that's 2/15 as well. And the probability of all being yellow, I'll colour code yellow in green, I know it's a bit confusing, but what the heck. That's 1/2 times 2/5 times 5/9. So 1/2 times 2/5 times 5/9. That's going to give us 1/9. So we've got 2/15 all over 1/9 plus 2/15. So this is going to be, well, I don't know, 2/15, and this one 1/9 plus 2/15 on the bottom, and we have 6/11. So probability of them all being red, if we're told, and we know that they're all the same colour, there's a 6 out of 11 chance that they're all red, as opposed to them being all yellow. And that's it from me. So there's 2 exam-based questions on tree diagrams. Now you need to try some on your own. So in your books, if you could turn to page 32, exercise 2E in the Stats and Mechanics Brown book, try questions 4 through to question 11, and double check as you're going regularly through the questions. Self-assess and ask me or someone who you trust if you are getting stuck. Keep plodding along, keep working hard, and you will reap the rewards. So once again, thanks for listening, and I'll see you all soon.